metric and what will be the Hausdorff space. So whenever you are going to work on fractals, then you must know about this space, the space where fractals live. So the outline of my talk consists of history, then definition of Hausdorff distance, then Hausdorff space, and completeness of the Hausdorff space. So this is the person, and the name of the person is Pompeo, and you can see his reference, and he wrote this paper in 1905, and he was doing something, and for that he needs some distance. So in his arguments in the complex plane, Pompeo needed a notion of distance between closed curves. Now you can see here, let E1 and E2 be two compact, compact means closed and bounded sets in the Euclidean plane R2, and if x belongs to E1, then we have to define some distance. Okay, so the first distance we are defining d of x comma E2, and this is like minimum of modulus of x minus y such that y belongs to E2. Then what will be d, capital D of E1 to E2? Okay, so E1 to E2 will be maximum of this distance, d of x comma E2. So what will be d of E1 comma E2 will be maximum of d of x comma E2. That's why we write, right? Maximum then minimum of modulus of x minus y such that y belongs to E2. Then the reciprocal or Pompeo distance P means this Pompeo has defined this distance. Like in Hausdorff metric, you know what is the Hausdorff metric. Suppose h of E1 comma E2, right? That will be maximum of d of E1 comma E2 and d of E2 comma E1. So in coming slides we will see that this Hausdorff metric or distance will be equivalent to this Pompeo distance. Okay, so first time he Pompeo described P of E1 comma E2 is equal to sum of these two distances, d of E1 comma E2 plus d of E2 comma E1. And for more reference you can see this paper from in 1806 by Jean Robert Argand. So I will go little further. Now you see here the one important property. If E1 is subset of E2, in both the figures you see. So in the first figure, two concentric circles are disk. So E1 is contained in E2. So the distance capital D of E1 comma E2 will be 0. In the second case also, means rectangle is inside the circle, there also d of E1 E2 will be 0. So if E1 is subset of E2, then capital D of E1 comma E2 will be 0. Then after that Frechet came. So already you know that Frechet introduced the definition of metric. So already you know that this is the preliminary what is the definition of metric. So let x be a non-empty set and let D such that x cross S to R, you can take R positive also, be a function that satisfied the following axioms. So first axiom is non-negativity, d of x comma y greater than equal to 0, and d of x y will be 0 if and only if x is equal to y. And the second property is symmetric property, d of x y is equal to d of y comma x. Then third property is triangle inequality, d of x comma z less than equal to d of x comma y plus d of y comma z. Then this d is said to be a metric on x, and the pair x comma d is called as metric space. And you can see the reference by M. Frechet in 1906 for this metric and metric space. Then after that this Felix Hausdorff came, and he has given one statement. In the natural setting of metric space S comma D with a small modification, the sum replaced by the maximum. Like in Pompeo what he has taken? D of E1, capital D of E1 comma E2 plus D of E2 comma E1. And now Hausdorff what is doing? He is just replacing with the addition he is replacing with maximum. Then H of AB is maximum of D of AB comma D of BA. So Hausdorff established that the Pompeo metric P of AB between compact subsets A and B of X gives the same topology as that of H of AB. That is, they are equivalent and hence called Hausdorff metric. So anyone can tell me the definition of equivalent matrix? Suppose we have two matrix D1 and D2, two matrix, and I want to say that they are equivalent. So I say that if D2 is equivalent to D1, then there must exist some constant C1 and C2. This happens, right? Clear? So now you have one Pompeo P metric and you have one Hausdorff metric. Okay, and you are saying that both are equivalent. Then we have to see that there are some constant C1 and C2 existing there or not. So here you see that how will you calculate D of AB and D of BA. So you see that blue color is B and that green color is A, and I just depicted, I was trying to show that means what will be the D of AB. So you see here this part is your D of AB and this part is D of BA. So like suppose you are doing PhD at IIT Madras or IIT Delhi and you have to give one comprehensive exam, and in comprehensive exam they check you very thoroughly. Okay, like again you are doing your GATE exam or JRF exam. So in that exam they give you all the syllabus of JRF and GATE and they will ask that what are you studying here? You say that fractal. So they know that fractals are living in the Hausdorff space. That means you know D of AB and D of BA. And in your DC committee member, suppose our means very reputed professors like Thamman Nair sir or Kulkarni sir is there, they will 100% ask these questions. Okay, I will give you one set A and B, you find D of AB and D of BA. So you just see that D of AB is nothing but supremum x belongs to A, infimum y belongs to B, D of x comma y. And we will see some questions. We will see some questions where we can see how we will calculate this. And this D of BA, supremum y belongs to B, infimum x belongs to A, D of x comma y. Now I am saying that D of AB is not equal to D of BA. Okay. So like that you can do one exercise here. Like Atanu is there and Atanu, I asked many times Atanu to do this type of exercises. Okay. So like you can see here, this is your A and this A is like x square plus y square is equal to 1, and this is your B and B is something x square plus y square is, let us say, 3 square. Okay. Then A is subset of B, right? A is subset of B. This means D of AB will be 0, but D of BA will not be 0. Okay. Where?
X square plus y square is equal to 1. It's just the boundary of the circle.
Ha. Now fine. Okay, so D of AB will be 0. Means I am just saying A is subset of B here. Okay. But D of BA will be some number greater than 0. So that means D of AB is not equal to D of BA. So like here I am saying D of E1 D of AB is not equal to D of BA. So now here we want to say that Pompeo Hausdorff metric. So like I told you that when two metric are equivalent, there must exist some constant C1 and C2. So I am writing this thing. You write maximum of 2 u comma v, maximum of u comma v is always less than equal to u plus v, right? Means 3 and 7. Then maximum of 3 comma 7 is 7, and that will be less than equal to 3 plus 7, 10. And this quantity will be always greater than the arithmetic mean, you can say, u plus v divided by 2, right? Now this will be, you said that maximum of d of a comma b and d of b comma a, right? This is your h of a comma b, and here d of ab plus d of b, means you write u as d of a comma b and v as d of b comma a. Then this will become h of a comma b, and this will become p of a comma b, this will become p of a comma b, and again this will become p of a comma b. So what did we conclude? That this is your C1 1 by 2 and this is your C2 1, like here I have written, right? So that means what? The Pompeo and Hausdorff metric both are equivalent. Anyone is having any doubt or question here? Clear everyone? So Hausdorff cited correctly Pompeo's contribution, and in this way he explicitly acknowledged Pompeo's superiority in the first edition of his book. Okay, so means Hausdorff clearly cited that this distance is discovered by Pompeo, and I am just doing the modification in that. Instead of plus, I am taking the maximum of these two things. Okay, so I will go further. So what will be the Hausdorff metric space? So let H of x be the collection of all non-empty compact subsets of the metric space x comma d. Then H of x over H, and what is capital H? H is the d of AB and d of BA maximum, forms a metric space called the Hausdorff space in general. Okay, so if you are a beginner in fractals or in zipper or anything in fractal geometry, these things you must know. Okay, especially like the person who are working in fixed point theory, they want to find some applications in fractals. Okay, so what we have to see, that first we have to see the non-negativity condition to prove that H is a metric. Then first you find H of a comma a. So H of a comma a is maximum of d of a comma a comma d of a comma a. So maximum will be d of a comma a, and that will be 0. So by compactness of a and b, so I will give you the reference of Barnsley book, and I have that book, I will share with you in the group. So in that he has mentioned several properties. So one property is H of AB is equal to d of some a comma b. For some a belongs to capital A and b belongs to capital B. So that means H of AB will be lying between 0 to infinity. Okay, and if a is not equal to b, we can assume there is a belongs to capital A, so that a does not belongs to capital B. It follows that H of AB greater than equal to d of a comma b, and that will be greater than 0. Okay, and like that we can show the triangle inequality. So all of you try this in your notes. I will ask one question and then you answer me. Okay, so how you are writing this step? It is straightforward, but all of you please answer me how you are writing this one. So all of you please try. So you have to prove H of AB. I am just giving you one. H of AB less than equal to H of A comma C plus H of C comma B. You have to prove this triangle inequality. H of AC is nothing but maximum of D of AC comma D of CA, and H of CB is maximum of D of CB and D of BC. So it is written here. Then from these steps how I am coming here, you please answer. Anyone? Is it straightforward to just apply the triangle inequality or something else more?
Using triangle inequality, D of A, comma C plus D of C, comma B, we will write it D of A, comma B, comma D of B, comma A. By using the Hausdorff metric definition, we
Mm-hmm.
get the answer. H of A, comma C plus H of B.
All of you try, all of you are getting this? Okay, so I am leaving this as an exercise, so all of you please see. Okay? How it will be less than equal to H of AC plus H of CB. Okay, it is looking straightforward, but it is not straightforward. You have to see. Okay?
What you see in terms of neighborhoods,
Yes, I am going.
much more simply.
Yeah, I am going to explain that. I am going to explain that. Okay? So the reference for this material is Barnsley book, Fractals Everywhere, and it is easily available online also. You can search it. Okay, so now I am going to give you the alternative definition as sir said in the case of neighborhood. So if x comma d is a metric space, then H of x I am defining C is a non-empty compact subset of x. And you know that what is 2 to power x or power set. Then I am defining the neighborhood n epsilon c. So n epsilon c means all the points in x, those who are having distance to c is less than epsilon, and c is coming from this capital C. And if c greater than 0 and c belongs to H of x, and I am defining H of AB in this way. Infimum of all those epsilons such that A is subset of n epsilon B and B is subset of n epsilon A. If A comma B belongs to H of x. Before we have defined H of AB is maximum of D of AB comma D of BA. Now this is another definition, and I am taking infimum of all such epsilon such that A is subset of n epsilon comma B and B is subset of n epsilon A. Okay, and the function h, this function h is a metric for H of x called the Hausdorff metric. So this will also be an exercise for all of you. You check that how this function h is a metric for H of x. Okay, so this is second exercise for you. So please cross check this. Then I am going further. So now I am claiming that both the definitions are equivalent. So how will we say this? For any given A belongs to H of x, let the epsilon expansion of A be the union of all epsilon open balls around points in A, and it is denoted by n epsilon A. That means n epsilon A is equal to union of such balls. Clearly H of AB is what you defined in previous slide. Infimum of epsilon greater than 0, A is subset of n epsilon comma B and B is subset of n epsilon comma A, is equivalent to saying that H of AB is equal to maximum of infimum of the same thing. Okay, means from this line, same line you write here and take the maximum here. Okay, then what you will get in the next slide. Now since you have taken what you have taken, A is subset of then what will happen? Then you replace, right? Wherever A is there, in this last line, A is subset of n epsilon comma B and B is subset of n epsilon comma A. Okay? Then you replace. Then you replace. Then you try. Are you able to follow this? All of you try this thing. Last line, are you able to follow? Clear? Anyone is having any doubt here? So that means that will become maximum of d of AB comma d of BA. Okay? Then we will go a little more further and we have one definition and one lemma. Let S is subset of K and let gamma greater than equal to 0, then S plus gamma. Okay, so what we are doing? We are doing the dilation. Okay, we are doing the dilation. So we want to find S plus gamma. S plus gamma, right? So S plus gamma is sometimes called the dilation of S by a ball of radius gamma. So what is the definition for dilation S plus gamma? It is nothing but y belongs to K such that d of x comma y less than equal to gamma for some x belongs to S. Okay? So please remember this definition, and I will share these slides today in your WhatsApp group so that you can follow them more nicely. So now you see lemma 1, let A and B belongs to H of x and H of x is your Hausdorff space where x comma d is a metric space. Let epsilon greater than 0, then H of AB, your Hausdorff metric, will be less than equal to epsilon if and only if A is subset of B plus epsilon and B is subset of A plus epsilon. Okay, so we will use this definition in our further results. So now you see A is subset of B plus epsilon. B plus epsilon means the set B is dilated by the radius epsilon, right? Clear? Okay, and you can see figures here, means figure B you can see here. I try to demonstrate that thing here in somehow. Okay, so now we go further. So the proof of this lemma will be very easy. So begin by showing that d of AB means what is H of AB? H of AB is maximum of d of AB comma d of BA. So first we have to see d of AB less than epsilon and d of B comma A less than epsilon, and we have to show that A is subset of B plus epsilon and B is subset of A plus epsilon. Then the other way we will show A is subset of B plus epsilon comma B subset of A plus epsilon, then we show that H of AB less than equal to epsilon. Then you have taken d of AB less than equal to epsilon if and only if A is subset of B plus epsilon. Suppose d of AB less than equal to epsilon, then apply the definition of d of AB. What was the definition of d of AB? It is maximum of d of A comma B such that A belongs to A less than epsilon. If the maximum of something is less than epsilon, that means d of A comma B less than equal to epsilon for all A belongs to A. That means what? For each A belongs to A, we have A belongs to B plus epsilon. That means A is subset of B plus epsilon. Suppose very elementary thing, if you say that A is subset of B, so that means what? How you prove A is subset of B? You take x belongs to A, and if x is in B, that means A is subset of B. So you take x belongs to A, then prove that x is also in B, then A is subset of B. So I am trying to do the same thing here. Okay. Now suppose A is subset of B plus epsilon, then what we have to consider? D of AB is nothing but, again I am writing the definition, maximum D of A comma B such that A belongs to A. Let A belongs to A, since A is subset of B plus epsilon, there is a B belongs to capital B such that D of A comma B less than equal to epsilon for all A belongs to A. Hence D of A comma A less than equal to epsilon. This is true for each A belongs to A. So d of a comma b less than equal to epsilon. Okay. So we have proved this lemma. Then we go little further. So like when you are studying some papers in fractals, in means our group or any group like Viswanathan sir from IIT Delhi and MGP sir from IIT Guwahati, okay, so they are using H of AB always, okay, but it is not like that. There is only d of a comma b, d of b comma and H of a comma b. There are many other distances also, okay. So if I define the first distance, you see, let x comma d be a metric space, and if a comma b belongs to 2 to power x power set, we define the generalized functionals d1 comma d comma h comma d2 and all from power set into power set 2 are plus as follows. Okay. So I am taking first distance. What is first distance? It is d1 a comma b. Okay. Before that d of a comma is here. We were till now we were discussing about d of a comma b and d of b comma a. So d of a comma b is clear to everyone, right? This thing is clear to everyone. H of a b is maximum of d of a comma b and d of b comma a. But there are two more distances, d1 and d2. Okay, so d1 is nothing but infimum of d of a comma b such that a belongs to a and b belongs to b. All this kind of distances and you take the infimum. Okay. So we will see like set A is here, set B is here, okay, set B is here, and there are many points, right? Infinitely many points here, also infinitely many points, okay. Then you are for each points you are finding the distances here. So there will be infinitely many distances and you have to take the infimum, okay. Then for any particular point, suppose if a naught belongs to x, then d of a naught comma b will be d of a naught comma b. Then what is the d2? D2 will be take the supremum. Take all the supremum. Here you have taken the infimum and here you have taken the supremum. So here d1 is called the gap functional between a and b. So d1 is called the gap functional between a and b. D is the excess functional, excess of a over b and b over a respectively, and h is, you know already, Pompeo-Hausdorff functionals, and d2 is called the diameter between a and b. Okay. So diameter means, diameter in real analysis you have learned about this, right? Maximum distance between two sets a and b. So I am calling it diameter between a and b. So I will go a little further and you see here. So recently my first PhD student B.V. Prithvi, and he defended his thesis. Now he is Dr. Prithvi. So he wrote one paper, interpolative operators, fractal to multivalued fractal, and it appeared in Chaos Solitons and Fractals in 2022. And we have given this type of one result to compare all kind of distances, which is greater than to which distance. Okay. So we found that d2 a comma b is always greater than equal to h of a comma b, and h of a comma b is nothing but maximum of these two distances, and here d of a comma b, d of b comma a, d of a comma b will be greater than to d of a comma capital B, and this will be greater than equal to d1 of a comma b. So you can see this paper and you see how we have calculated these things. And I will take one or two examples in my future slides, and I will show you some things to you can relate here. Okay. So like I have taken a set A and set B, and set A is here and set B is here, and I am taking only finite set. Okay. Set A are having only 5 points, A, B, C, D, E, and B is also having some finite points. Means here I have showed infinitely many points. It will be difficult to calculate, right? So first we understand for finitely many points. So you see here I am finding d1 a comma b. So d1 a comma b means minimum of distance of d of x comma y such that x belongs to a and y belongs to b. This means minimum of d of a comma b, all the points, right, in b, in a, from a to b, B to B, C to B, D to B, and E to B. Okay, like this one. Then you can find here D of AB, D of BA. D of AB means maximum of these things. D of BA maximum of B, F to A, G to B, H to C, I to D, J to E. Okay. A simplest examples I can show you here so that you can start visualizing the things and you can relate. Okay. Then H of AB will be maximum of these two distances D of A comma B and D of B comma A. Then what will be D2 of A comma B will be maximum D of X comma Y such that X belongs to A comma Y belongs to B. Okay. So there are some more things. So all of you first check that I take a space X is equal to 1 2 3 and I define some distances like D of 1 comma 1, D of 2 comma 2, D of 3 comma 3 0, D of 1 comma 3 2, D of 1 comma 2, like that. Is this a metric? Is this a metric? So when you are working on fixed point theory, then you can propose the theory, but examples are always valuable. Okay, right? Means fixed point theory only work on examples, right? If you give the nice examples, then your paper will be published in very nice journal. Okay, so first you cross check that is this a metric over X is equal to 1 comma 2 comma 3. And if I increase the points here, like I take 10 points, then it will be difficult to construct. Okay, and suppose now when Prithvi and Kifayat were defending their thesis, then some professors came from IIT Madras. They were asking that why you are taking finite set. For finite set also to create a metric it is difficult task, and if you take infinite set then it will be more difficult. Okay, so please cross check that is this a metric. Okay, and I assume that suppose this is a metric. Okay, then हाँ 2-3 की डिस्टेंस आप इसलिए मैंने छोड़ रखा था यहाँ पे कि कोई बताए. ठीक है, तो मैं 2-3 की यहाँ डिस्टेंस नहीं दे रखी है. 2-3 की डिस्टेंस आप देख लो, 2 ले लो या ठीक है ना. तो यहाँ पे क्या है, यस वी हैव नॉट टेकन द डिस्टेंस ऑफ 2 to 3. So D of 2 comma 3 and D of 3 comma 2 will be 2. You take, assume. In next example I have put this thing. Then what will be D1? D1 is not a metric. So what was D1? D1 was infimum of D of X comma Y. So D1 is not a metric. Then you see H of X. H of X will be all 1 to all the singletons. Then 1 to 2, 1 to 3, 2 to 3, then 1 to 3. Then find D1. So I am just telling you how to find D1. D1 1 comma 2, 1 comma 3 will be infimum of D of 1 comma 1, 1 comma 1, 1 comma 3, 2 comma 1, 2 comma 3. Then infimum, whatever distances it is given in the question or in example you put here 0, 2, 1, 0, take the infimum, the answer is 0. So I am giving you one example how to find D1. Okay. And 1, 2 and 1, 3 are distinct elements, but the distance is 0, so that D1 is not a metric. You got the point? What is the metric definition? D of X comma Y is equal to 0 if and only if X is equal to Y. And here you are getting D1 of these 2 points is 0, but this is not equal to this. So the first definition of metric is not fulfilling. That means D1 is not a metric. Now we'll say same way you can say that D2 is not metric. D2 means what? Take supremum, then H of X. And here also we have found the D2. D2 of 1 comma 2 and 1 comma 2, same point I have taken. And you are saying that here you are getting, you must get 0. If D2 is a metric, then you must get here 0. But you are not getting the 0. You are getting the 1. Okay. So that means D2 is also not a metric. Okay. Then we go further. And these are the properties of Hausdorff metric. So means some of the properties I have quoted here. If A belongs to closure of A, if and only if D of A comma capital A is 0. and D of A comma capital A is equal to 0 if and only if A belongs to A. Huh? So this type of properties you just verify. I will give you these slides, like D of A comma A less than equal to D of A comma B, D of A comma A is equal to H of A comma B if and only if A is subset of B. Okay, so these properties we will use when we will prove that Hausdorff space is complete, okay, or compact. Then this type of properties we need. So you just go through these properties and try to verify by your own. And now I have given another example. So like my student Deepak says that here D of 2 comma 3 and 3 comma 2 is not defined. Okay, so I just put here D of 2 comma 3, D of 3 comma 2 is some number 2. Okay, then you find what will be the Hausdorff space. Then I said that 1 2 3 1 2 3 1 2 1 3 2 3 1 2 3 with Hausdorff metric H. Then I am trying to find that what will be H of A comma B. This is your A, this is your B, and this will be maximum of D of A comma B and D of B comma A. So D of this one and D of this one. Now you find D of 1 comma 3. Then D of 1 comma 3 will be maximum, minimum, D of 1 1 and D of 1 comma 3. Okay, but D of 1 1 same to same point will be 0, and D of 1 comma 3 you define somewhere as 2. Then minimum of 0 comma 2 is 0. Then you are getting 0. Then same way you find D of 1 comma 3 1. Same way you find, you will get the answer as 0. Okay, so I am just demonstrating how to find these things. Okay, so then H of 1 comma 3 will be maximum of D of A comma B and D of B comma A, both were 0, so you will get the 0. Like that you can see. Okay, you can find H of some A comma B, right? So in both the examples, H of A comma B and H of B comma A, right? They must come same. Why they must come same? Because H is the metric. Before it is not coming. No, some properties we were not getting correct. But H is a metric. H is a metric. So H will satisfy all the exams of metric, right? So now means you can take some interval kinds of things like closed intervals. So let X is equal to R, B metric space endowed with usual metric D, H of X is Hausdorff metric space with Hausdorff metric H, and now I am taking closed intervals A comma B, C comma D are element of H of X. Then what will be H? I have given Atanu these exercises that suppose 0 comma 1 and 0 comma 2 and this is 1 comma 3, what will be H of A comma B, and like 0 comma 2 and here 3 comma 5, then what will be H of A comma B? Means you just create many examples, right? When two intervals are overlapping or two intervals are disjoint, if one is half is subset of other, something like that. Okay, so here you see what will be H of A comma B comma C comma D will be same way. Then this will be D of A comma B C of E, this one. Okay, this will be maximum minimum of D of X comma Y, such that this happen, and here also like this way. So we are trying to calculate this. We are trying to calculate this, and if you are not able to understand these things, then you just simple examples. Okay, take some closed intervals 0 comma 1 and another interval 2 comma 3 and see that sometimes they are overlapping, some they are not overlapping, sometimes they are disjoint. Then try to find what will be D of A comma B, what will be D of B comma A, then find H of A comma B and H of B comma A, like that. Okay, then slowly you will become master in that. So I have taken all of you, please verify this. Don't see the slides. You just take one interval 1 comma 2, another interval 3 comma 4, and then find the H. Okay, please don't see these answers, just see this line. Just see this line. First your interval is 1 comma 2, another interval is 3 comma 4, then please find H. Please find H. So if anyone is having difficulty, then please ask. And if you are having any difficulty, then you can see my slide. Everyone got this? Okay, meantime I can clean my board. Done. Everyone? Okay. So this is your extension lemma, and it is given in Barnsley book, and I just read it. Let x comma d be a metric space, and let an be a Cauchy sequence of points in h of x comma h, and let n and j be an infinite sequence of integers, and they are increasing 0 less than n1 less than n2 less than n3. Suppose that we have a Cauchy sequence x and j belongs to an, and that belongs to x comma d, then there exists a Cauchy sequence x and j bar that will be equal to x and j. Okay, for all j is equal to 1 2 3 so on. Okay, so how to prove this, and to prove this, like, so you always see this type of things. Okay, so suppose we want to find the distance between xm bar comma xn bar, then you just apply the triangle inequality and try to break it, right? So d of xm bar to some xnj, and xnj to xnk, and xnk to xn bar. Okay, and now you have to find this thing something epsilon by 3, this thing some epsilon by 3, and this is epsilon by 3, and when you add together, then this will become less than epsilon at the last. Okay, so now we have to see this one, and this one. Okay, so I will give you these slides, and you can see means what we are doing here, means how we are selecting nj and nk, and we are defining these distances. Okay, so I will give you these slides. And now this is our last theorem, completeness of Hausdorff metric space. So let x comma d be a complete metric space, then h of x comma h is also a complete metric space. Moreover, if an belongs to h of x is a Cauchy sequence, then its limit, its limits must also belongs to h of x. Okay, so that is the property of complete metric space, means if a sequence xn is there and if x1 converges to x, then x must belongs to that space. Okay, so this theorem or material I have taken from Barnsley book, so I will share with you. And how to prove this result, and to prove this result we have 5 steps. Like, first we have to prove that A must be non-empty, then we have to prove that A is closed and hence complete since K is complete. Then we have to the extension lemma, we have to apply the extension lemma. For epsilon greater than 0 there is n, such that for n greater than equal to n, A is subset of an plus epsilon. Then we have to prove that A is totally bounded, and thus by B part it must be compact, and then we show that limit an is equal to A. Okay, so I just give you this slide so that you can go through it, or you can see the Barnsley book. means how we are proving point A, point B, and then C, and then we are combining all these things, and then we are saying that this H of x comma H is a complete metric space. Okay. So thank you, and now I will go for my another presentation. So I will talk about some fractal interpolation or fractal functions here. Okay, so now you are able to see this figure. So fractal functions are very irregular in nature. Okay, now you see this figure here. You see 1, 2, 3, 4 points, and so the curve is very differentiable or non-differentiable. So the curve is very non-differentiable. Okay, and here when I am choosing alpha is equal to 0, then this is smooth. Okay. So now we will talk about this means, and we will see also how to plot these figures. So take the data xn comma yn belongs to R2, and I am taking this notation n belongs to nn, means 1 comma 2 comma 3 up to n. It means you can say that first n natural numbers here, nn means first n natural numbers. Okay, where abscissae are strictly increasing in order, means x1 less than x2 less than dot 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 xn, and I take ln such that I close interval to its subinterval in xn comma xn plus 1 be contraction homeomorphism satisfying ln x1 is equal to xn and ln xn is xn plus 1. So these things will be little important, so just I note them down. Ln such that I is our x1 comma xn to in, and in is nothing but xn comma xn plus 1, and here n belongs to nn minus 1, right? And I am saying that is a contraction homeomorphism. Contraction you already know, the definition of contraction you know. And what is the meaning of homeomorphism? Homeomorphism, when a mapping is homeomorphism, when it is bijective and it is continuous and its inverse is also continuous. Okay, so ln is a mapping which is continuous, ln is bijective, and ln inverse is also continuous. Okay, and it is satisfying two conditions, means ln mapping first point x1 to xn and ln mapping this end point xn to xn plus 1. Okay, then I take suppose 0 less than equal to rn less than 1 and consider continuous maps fn, and fn satisfying two properties. Fn of x1 comma yn is yn, and same thing. Okay, here x1 first point we are saying no, so x1 and corresponding y1 is going to yn, and fn xn comma yn is going to yn plus 1, and fn is contraction in second argument. Okay, fn x comma y minus fn x comma y star less than equal to rn y minus y star. So I am saying that fn is contraction in second argument. Then I am taking one collection I cross r comma wn, and in wn I am putting ln comma fn. Okay, so I am calling this as iterated function system, or in short I call them as IFS. Okay, now I construct a metric space. So I take script g as some continuous functions, and they are satisfying h of x1 is y1, and you see that when this construction was made by Bansley sir, so x1 means xn is must go to yn, right? So based on that he is mapping x1 to y1 and xn in point to yn. Be endowed with the uniform metric. So you already know what is the meaning of uniform metric, right? Maximum or supreme norm you can define. Then T such that script G to G be defined by TH of x is equal to in this way. So I am writing th of x is equal to fn ln inverse x and comma, what can you write? h naught ln inverse x. Okay, and for all x comma x belongs to I. Now we have to prove that this T is a contraction mapping. Okay, so how will you prove that T is a contraction mapping? So like here I can write th of ln x. So you will get, what will you get? Fn, yes, what will you get? X comma h of x, right? Okay, then similarly you write some tg of ln x, so tg of ln x will be fn x comma g of x. Okay, then try to find tg of ln x minus tg of ln x. Okay, and if you are taking infinity norm or means whatever, okay, then what will you get here? Fn x comma h of x minus fn x comma g of x. Okay, but you said that fn is a contraction in second argument in previous slide. Okay, so fn is a contraction in second argument, then what can you see? This one, fn is a contraction in second argument, so it will come less than equal to Rn times. Okay, Rn times what will you get? H of x minus g of x. Okay, and by that you can prove that th minus tg less than equal to r times or Rn times whatever, okay, h minus g. Then this will be one more exercise for all of you. You just try to think and let me know in the after lunch that here I am taking ln x, right, and here I am writing free from ln. Okay, so how is it happening? Okay, so you got that T is a contraction mapping, and your script G is a complete metric space. You can easily prove this, that script G is a complete metric space, and you are defining a mapping T from complete metric space to complete metric space, and T is also a contraction mapping. So by Banach fixed point theorem, T will be having a unique fixed point. So this equation th of x will be what? H of x. Okay, but th of x is what? Th of x is fn ln inverse x and what? H naught ln inverse x. Then you take h of ln x. H of ln x will be what? Fn x comma h of x. So you got this one. So this h is nothing but your, what is h? Okay, so now here so most means extensively stirred fractal interpolation functions so far are defined by the IFS. They take ln x is equal to what they take? an x plus bn or en. Okay, and fn xy they take alpha ny, fn xy they take alpha ny plus qnx, right? Qnx. Okay, then put this value here, then what will you get? Your h of ln x, what will you get? H of ln x, what will you get? Fn x comma h of x. So what will you get? Alpha n y is h of x plus qn of x. Okay, so meantime you have seen many papers, someone saying that affine fractal interpolation function, someone is saying cubic, quadratic, rational, trigonometric. Okay, so they are just depending on this qn, your qn such that I to r. Okay, if you take qn is affine map, okay, affine map. Let us say Qn is equal to some, I have taken Anx plus En, then you will take something, whatever, anything you just tell me, Cnx plus Dn type, okay, and you replace here, then this will give you a affine fractal interpolation function, okay, affine fractal interpolation function. Okay, or affine FIF. And if you take Qn as a quadratic function, let us say Qn is equal to Cn x square plus Dn x plus some Fn, okay, then this will give you quadratic fractal interpolation function. Someone will say that, sir, I will take Qn is equal to some Pn theta by Qn theta, okay, then he will get rational fractal interpolation function. Someone will say that I will take Qn as some trigonometric polynomial, okay, trigonometric divided by trigonometric, okay, then what will we get? Rational trigonometric FIF. So whatever Qn you can choose, okay, you will get that kind of fractal interpolation function, okay. So now this construction was done by Barnsley sir, then came Navascu madam, Maria Antonia Navascu from Spain, University of Saragossa, and what she has done, she is saying that I will take Qn in this way, okay. So I just show you that what will happen after that. So you just take Qn as f naught ln x minus alpha n b of x, okay. So before that you take let f belongs to C of I, and you take Qn in this way, then put, let us say this equation is star, put the value of Qn, then what will you get? H of ln x is equal to alpha n h of x plus put the value of Qn. So what will you get here? F naught ln x minus alpha n b of x, okay. So somewhere I means here I am taking g, right, and here I am taking h, okay. So anywhere. So if I replace here ln inverse x, so h of x will be alpha n, yes, h of ln inverse x, right, plus what will you get? F of x, then minus alpha n b of ln inverse x, okay. And this I am denoting as f alpha, right. So further they will get f alpha x, and this one you combine, and this one you leave here. So what will you get? F alpha x is equal to f of x plus alpha n times last line, okay, f alpha minus b naught ln inverse x, okay, and for all x belongs to in and n belongs to nn minus 1, means whatever h you are getting, that will become f alpha, okay, as a notation, just as a notation, okay. F alpha is nothing but your h of x, Okay, so just notation I am writing f alpha x is equal to f of x plus alpha n into f alpha minus b not ln inverse x for all x belongs to in. Okay, and here b is your base function. B is your base function. B is base function means b x1 is equal to f of x1. What f you have taken? B of xn is equal to f of xn, and b is not equal to f, means this point and this point, f can be like this, f can be like this, and b can be like this. This is b. They are matching these 2 points. They are matching these 2 points, but they are not equal. They are not equal. Okay. So by this what did you understand? By this what did you understand? Anyone? By this what did you understand? Abhijit? What did you understand by this? Anyone? Any idea? You have taken any f belongs to C of I, correct? And for that you are getting a fractal function. Okay. So for any continuous function you are getting a family of functions f alpha always. Okay. So when this thing came, then our fractal got more popularity, because you are now getting a family of fractal functions, right? What happened? Source? Huh? Sakshi knows, I think. Source. It will come. Okay, so for any continuous function f, you are getting a family of fractal function f alpha x is equal to f of x plus alpha n f alpha minus b not ln inverse x. And your alpha is what? Alpha is your scaling factor, right? And alpha by contraction condition it must lie between -1 and 1. Now you have many alpha. You have many alpha, means alpha ranging from -1 to 1. And in this equation if you put alpha is equal to 0, means you have range from -1 to 1, right? Alpha values, infinitely many values you can take. Okay, and somewhere here alpha is 0. So if you put alpha is equal to 0 here, then f alpha is nothing but f. Alpha fractal function is nothing but only f. And if you vary your alpha in the range -1 to 1, you will get a family of alpha fractal functions, means you will get infinitely many alpha fractal functions. So now the thing is that suppose I take here, okay, I take 4 points. Okay, now Dr. Vijay will go for interview, okay, many places. So they will ask such type of questions. They will ask that already interpolation theory was there, okay, why did you bring this fractal interpolation theory? What is the difference? Okay, so what you have to answer that. Suppose we have 4 points. Suppose you have 4 points and you take polynomial interpolation or zipper interpolation or anything, okay, and you draw a curve, right? Okay, you draw a curve passing through these points. This is the interpolation theory, right? Now I want a curve. Now I want a curve like this one. Okay, so what you drawn before, that curve is unique by interpolation theory. Now I am saying that you draw this curve. Now you draw this curve passing through these 4 points. Then what will you do? What you have drawn, that was unique curve. Okay? Now I am asking another curve passing through those points. Then what will you do? Either you change your polynomial interpolation to some other, like you replace by trigonometric, rational or something. Okay? Or you change the points. So what will you say? I will take first point here, and instead of taking second point I may shift here, and third point I may take here, and fourth point as it is. Okay? Then I will apply hit and trial method, and I will see that my curve is passing through these points or not. Okay? But when Navascuum introduced alpha fractal function, now you have alpha ranging from -1 to 1, and you have infinitely many choices. Okay? And by choosing alpha from these same points, how many different curve you can, infinitely many curve you can draw, right? Okay? And maybe the curve asked by someone may coincide here for different value of alpha. Understood? And when you are taking alpha is equal to 0, then whatever classical interpolation theory was there, you will exactly get that theory. So what you got? That this fractal interpolation function, your alpha fractal functions, they are generalizing classical interpolation theory. Okay? And in the same time, by varying the value of alpha, you can get infinitely many curves. Okay? And the other thing is that I have showed you first picture. I will come it again after tea break. So classical interpolation theory only work for smooth data points. Okay? And if you have very irregular data, okay, your guide is also working on the same thing. These three persons from NIT Trichy and Gauri Shankar also. Okay? So means when your data is very irregular, suppose we are at NIT Jalandhar, and I just say that now onwards to 15 seconds or 20 seconds, we have to see the load of intensity at NIT Jalandhar. We have to measure the load of intensity at NIT Jalandhar. Okay? So suppose we are in this room, all the fans and all the things are working, but her guide, Mary Samuel madam, is inside the Mega Girls hostel, and she may be opening her laptop, or she is switching off or on the AC or fan or something. Okay? So the load on the intensity will be like this, no? Like suppose earthquake coming here, okay, and you want to measure the intensity, then the curve will be like that. It will not be smooth, very irregular, and you want to interpolate it, then classical theory again will not work. So wherever irregularity is coming, or any function is there that is smooth, but you are finding the derivative of that and it is becoming irregular, then again classical theory will not work. Then you have to see your answers in the fractal theory. So I just stop here and we take a short break of tea. Then we will meet again and discuss some more things. And then I will hand over to sir to give some more insights in that. Okay. Thank you.